This is my hi. This is my submission for the competition. I just wanted to go through it here because I was pretty upset with how it came out looking in like the web viewer for GitHub. So I really want to talk about what I've done. So this is my submission. So introduction, just an overview of the problem approach, and I mentioned the two methods that I use, which are a predictive model called edge memory neural network, which learns directly on graph structures, which can be found here, and also a constrained graph variational autoencoder, which can be found here, which is the generative model. So I use both a predictive model and a generative model in my submission. So the predictive model I use to predict, I take some similar compounds similar to the N3 ligand, and then I predict what their activity is going to be. And then for the generative model, I generate brand new compounds based on a data set. And so I'll talk about that data set as well. And then also I finish up by, with my new compounds, I dock them in Autodoc Vina and then take the scores for the best ones. I don't need the kernel because I'm just walking through what's already here. So the highest scoring candidates are then talked about. So disease and background, here's a visualization of the actual compound in the binding pocket of the protein. And I get a couple, and here I map out a few of the interactions. And then now the first thing to do is downloading the data set. So I go to NCBI PubChem to download different assays based on different targets. So I searched various different kinds of targets to get different assays. And then I had a large list of assays. So here, this is a function to get assays and then get the actual molecular structures for each of those assays, because the assays don't have like smile strings in them. They only have compound IDs. So that just is another way to get them. So yeah, with the data set loaded, we also need to prepare the PubChem standard value. So this is the activity. So you should watch my other video on activities to kind of talk about which activities I chose and why. But here you can see this. I was very unhappy with how this came out, because here you can see on my screen it's like a little window, but on the web viewer for GitHub it is the whole list, and it's gigantic. Anyway, so here's the various data, and then here's method-specific data preparation, which just prepares the data to be like exactly the format that's desired for each of the two methods. And then the first method is the bioactivity with the edge memory neural network. So here the model is defined, and you should really check out this paper, because like I'm not going to try and claim that I wrote most of this. It was an excellent master's thesis by this gentleman Everard, and it's great. Yeah, you should check it out. Anyway, so yeah, this is just the implementation of it. And then my final data set was about 6,500 compounds with activities, which is good. And that's with activities below 1 micromolar. I set a threshold. So we're really getting active compounds for the prediction. So that's good. And then we train here, prediction. Yeah, so train up to epoch 10. And then we make some predictions based on that. So you can predict using this is already stored in the saved models if you want to make predictions based on that instead of running it. And yeah, and then so you can add here, see this predict. So this is predicting off of like the built-in test set. But then I also go online and I get compounds similar to the N3 ligand, and then I then I download them, and then there's about 180 of them, 180 or so, and then I predict the best ones and take the 10 best ones, and those are the ones that I save to be docked. So here you can see I keep 10 best ones and then store them to be docked later. And so for the second method, the variational autoencoder, this is where we're actually dealing with a generative method. So this is using TensorFlow. The two methods, one uses PyTorch, one uses TensorFlow. I don't like it, but that's the way it has to be. So yeah, train validation split to kind of prepare the data. This is very much jerry-rigged to be to work off of what their data has, or the way that their submission, like their GitHub repo works. So you'll see the data being named strange things. For example, valid ID zinc. That's because I'm using the implementation for their zinc database for my own database. And you can see that in the submission as well. And then here, preparing the data, you can see it being prepared here. And then here are the various arguments for the model. And then here you can see it runs. And then it was running, but but I stopped it with the keyboard interrupt because it takes a very long time. But here you can see that it actually can successfully restore weights from files. So if you go into the data, you can see this file, which is when I trained it for 10 epochs already. That's how I generated the compounds. So you can go check that out and generate your own if you'd like. And so for validation, first thing I did was redock the molecules using Autodoc Vina, which you can see here. Here's a full description on how I did it. I wanted to make a video, but didn't have time to. And then there's what the N3 ligand looks like. Here's it redocked. It's very different than the structure from before, but that's what it looks like. So yeah, and then preparing preparing and the high scoring and the generated compounds for docking. So then I just made some scripts to kind of write them to PDB files for docking, and also to this writes the configuration file that Autodoc Vina will actually read and to dock the compounds. And then still here are the scores for the various compounds. So here are for the predicted compounds. So keep in mind that these are predicted to be the 10 best using the predictive model, and then these are their actual docking scores. You can see the numbers there. And you can see that there are some good ones. I think the best one here is minus 8.7, and that's compared to the N3 ligand, which is minus 7.9. So it's predicted to be better than the N3 ligand. And then so yeah, here are the generated compounds, and you can see they are there's some strange looking structures with these large ring structures and stuff that doesn't make any sense. But yeah, so but there are a couple good ones. So I took like the 10 seemingly reasonable ones, like for example that guy, and then basically when it doesn't have a giant ring, and that one, and I use them for docking. So there's the indexes for like the 10 most reasonable ones, and then writing the score, writing the configuration files. Yeah, I already talked about that. And then here are these ones, I believe, are the generated ones. So these are the dock generating ones with their docking scores. And so the best docking score of anything was minus 9.8, which is, so here the best predicted and the best generated. Here is a picture of the best predicted one in the binding site, and you can see that there's plenty of interactions between those residues. Here, the best generated one, looking excellent in the active site. And keep in mind that this is the highest score of all of anything of anything that I've tested. And so yeah, discussion and conclusion. So yeah, there's these two compounds are basically the two ones. So this one had a much higher docking score than this other one, but both of them had a higher docking score than the N3 ligand. But I would recommend actually the predicted one be investigated. That's because it came from PubChem, so it has to exist. Like someone made this and put it on PubChem. So that's why there's a better chance that it will actually exist versus this other one, which may or may not exist, or like may or may not. It might take years to synthesize properly. Who knows? An experienced chemist would have to tell you. Yeah, and so that's my implementation. So thanks a lot to everyone who created something that I use. So like Vina, Schrodinger, the two papers and their authors are great. And thanks to Sage Health and Suraj for the opportunity for the competition. And thanks for anyone who got this far in watching.